So thanks for your patience in the first two chapters as we were developing the mathematical foundations necessary to study electromagnetic field theory. Now we're going to begin to study electromagnetics proper. We're going to look first of all at Coulomb's law and the force between two charges. We're also going to study the electric field that's created by a charge and how it can impact other charges that are nearby. So we're going to use Coulomb's law to first of all determine the force exerted by one electric charge on another, determine the electric field surrounding a point charge, determine the force on a charge due to an electric field, and use superposition to determine the electric field due to multiple charges. It's just good to know that the person who originally formulated Coulomb's law, of course, his last name was Coulomb, Charles-Augustin de Coulomb. Not only did he do work in electrostatics, but he also did work in friction. In the late 1700s, it was a time when you could make a lot of progress in a lot of different areas. Not only does he have Coulomb's law named after him, but he also has the fundamental unit of electrical charge. The Coulomb is named after him as well. So let's talk a little bit about charge. Charge is something that a piece of matter exhibits. It's not related to its mass. It's not related to its density. It's not related to its color. It just depends on what is the charge of that particular piece of mass. Charge is really composed of protons, which have positive charges, and electrons, which have negative charges. Nearly every phenomenon we're going to study in this class arises from interactions of electrical charges. First, we'll talk about what happens if the charges are sitting still, in other words, electrostatics. Then what happens if they're moving at a constant velocity, which we'll call magnetostatics. And then we'll look at what happens if they're doing even more complicated things like accelerating and decelerating. Now, the fundamental SI unit for charge, of course, as I just mentioned, is the Coulomb, which we'll abbreviate it with the capital C. It turns out that a Coulomb is a very large amount of charge. If you think about the fact that both an electron and a proton, they each have 1.6 times 10 to the minus 19th coulombs of charge, this means that 1 coulomb of charge contains more than 10 to the 18th electrons or protons. And I've written that out, and it's over 6 quintillion individual charges. A lightning strike, one of the most powerful examples of electromagnetics that we can see in nature, really only contains about 10 to 20 coulombs of charge. So think about the destructive power of lightning and realize that might have only been 10 coulombs of charge. Really puts things into perspective when you think about that. For example, if you turn on a 100-watt light bulb, you're drawing about 1 amp, which means that about 1 coulomb of charge is flowing to that light bulb every second. Or over the course of 10 seconds, you're harnessing 10 coulombs worth of charge. Every 10 seconds, that light bulb is absorbing the amount of charge that would be present in a lightning strike. We'll talk more about that in a little bit, but it's really remarkable how much charge we often work with and we take it for granted. Now, we're going to introduce just a handful of universal rules in this class. One of them, the very first one we're encountering is today. Universal rule number 1, electric charges always exert a force on each other. Doesn't matter if they're sitting still, doesn't matter if they're moving at a constant velocity or accelerating, they always exert a force on each other. Now, the magnitude of that force and the direction of that force can be determined by Coulomb's law, which is shown here in this first equation. You can see that there are two charges, Q1 and Q2. There's the distance between them, r squared. There's this constant, 4 pi epsilon 0. And we'll talk about why the 4 pi is separated out in a little bit. Not today, but a little bit later. And then we have the unit vector a sub r, which determines the direction that force is taking place. Now, this constant epsilon 0 is referred to as the permittivity of free space. And it has a value of 8.854 times 10 to the minus 12 farads per meter. That's a weird unit, I understand. There are other ways that we could express it, but none of them are as compact as that. I'll just say that if you use Coulomb's law or any of the other laws we're going to talk about, and you use the correct units, which is to say coulombs and meters and so forth, and you plug in this constant at that quantity, then the output is going to be the correct unit as well. And typically for force, that would be, say, newtons. This 8.854 times 10 to the minus 12, you're going to use that so often that it's really going to become part of your short-term memory. You'll be able to pull that out anytime that you need it. So as I mentioned, we'll talk about why that 4 pi is separated out. That's coming up in just a couple of chapters. The unit vector is an important part of this, because remember that Coulomb's law, not only does it specify the magnitude of the force, but also the direction of the force. And so you can see here we have an equation that identifies what is that unit vector, where R1 is the location of the charge that is, quote, causing the force, and R2 is the location of the charge that is, quote, feeling the force. Now, we understand that in reality, those two forces are both causing, those two charges are both causing a force on the other charge. But typically we will be considering one charge to be fixed or creating the charge, and the other creating the force. We'll look at the other charge as saying what is the impact on that charge. So the equation and the constant epsilon 0 again are set up so that if you use coulombs and the distance is in meters, then the force will be in newtons. So let's look at an example here. What is the force exerted by charge B on charge A in the following figure? So we're going to say that B is fixed. In other words, we're going to say that really B is not going to have any, it's glued to the wall, or it's sort of penned in three-dimensional space. And we think about, well, what would happen to charge A caused by charge B? Well, we can see that they have opposite charges. And we also know that if the charges have opposite polarity, they're going to be attracted to each other. Whereas if the charges have similar polarity, both positive or both negative, they're going to tend to be repelled from each other. So we're going to see that this charge is going to be attracted toward charge B. And so we can ask ourselves, whoops, sorry about that. We can ask ourselves what is going to be the magnitude of that charge, and then mathematically what is the direction of that charge. And we can calculate those quantities using the equation that we've already seen. So let's consider what is the vector R2. So R2, if I look up here, R2 is the location of the charge that is feeling the force. And in this case, clearly the one that is feeling the force is A. So we're going to say that R2 is equal to RA, which is just going to be 2A sub x plus 5A sub y. And we're going to say that R1, which is the location of the charge that is causing the force, this is R sub B, and this is going to be 4AX plus 3AY. And then, of course, the vector between those, R, is going to be R2 minus R1. And you might be thinking at this point, you are really putting a lot of detail into this, and you'd be right. It turns out that only by putting this level of detail into the calculation are we able to ensure that we're going to get the direction correct. Now, in this example, we'll be able to verify that the direction is correct, but in some future examples, it'll be three-dimensional and complicated, and we won't necessarily be able to be certain that we got the direction correct unless we do it with this level of detail. So when I have done this subtraction, I end up with the fact that the R is negative 2A sub x plus 2A sub y. And in other words, the R is pointing, so I should clarify, F is pointing this direction, but R is pointing in this direction. R is always pointing from the particle that is causing the force up to the particle that is feeling the force. And so here I'm going to show R going that direction. So what is the magnitude of R? Well, the magnitude of R is just going to be the square root of negative 2 squared plus 2 squared, which it turns out is the square root of 8, which is 2.828, and therefore A sub R is just going to be R divided by the magnitude of R, which is negative 2A sub x plus 2A sub y divided by 2.828, which it turns out is minus 0.707 A sub x plus 0.707 A sub y. So that's the direction of the force, and that's the unit vector that's pointing in the direction. But the force in this case is going to be Q1 Q2 divided by 4 pi epsilon 0 r squared times A sub r. Well, Q1 is going to be positive 2 coulombs, and Q2 is negative 3 coulombs, and that's all divided by 4 pi times 8.854 times 10 to the minus 12th. And then in the radius is going to be, as we just saw, 2.828 squared. That's in meters. And then if we multiply that by the unit vector, minus 0.707 a sub x plus 0.707 a sub y. Finally, we're going to end up with the force being 4.77 times 10 to the 9th a sub x minus 4.77 times 10 to the 9th a sub y, all of this in units of newtons. So that is the magnitude of the force between two charges, one of 2 coulombs, one of negative 3 coulombs. And if we look at this, we can see that this has a positive x component of the force and a negative y component. And when I come back up here and I look at the force that I originally sketched, it has a positive x component and a negative y component. So I'm feeling pretty good about this. Let's take a minute and just think about how big these numbers are. Of course, the size of these numbers is largely coming from this 10 to the minus 12th right here. That negative 12 in the denominator becomes a positive 12 in the numerator. But let's just take a minute and consider, think about the Sears Tower. If you do the research and the Sears Tower weighs 222,500 tons, which is 4.45 times 10 to the 8th pounds, which is about 2 times 10 to the 9th newtons. So that means that these numbers are more than twice the weight of the Sears Tower. So we're talking about two relatively small charges, 2 coulombs and negative 3 coulombs, that are of space of a couple 3 meters apart. And we're talking about the amount of force between them is twice the weight of the Sears Tower. It would be practically impossible to keep these two forces away from each other. They're going to fly toward each other no matter how hard we try to prevent it. But it's just good to have that scale of how big are these forces that we're talking about. We're talking about extremely large forces, and that's because a Coulomb, again, is a very large amount of charge. Okay, so we can use Coulomb's law all day, but it is pretty complicated. And the reason for that is because there are 2 different charges to keep track of, each of which has its own magnitude and each of which has its own location. It would be a lot easier for us if we only had one quantity to keep track of, or one charge and one location. It would be acceptable. And the electric field allows us to do that. What we do is we temporarily remove the second charge, the one that feels the force, and we ask ourselves what would be the force on a theoretical charge if it were placed at every possible location around the first charge. So again, we have the fixed charge. We're going to put it in space and it's going to stay there no matter what. And then we're going to look around that charge and we're going to imagine, what if I put a 1 Coulomb charge here? What if I put a 1 Coulomb charge here? What if I put a 1 Coulomb charge here? How much force would be at each of those points? And that's what the electric field does for us. Now, I mentioned that we were going to use a 1 Coulomb charge. We could, of course, use a 10 Coulomb charge, but if we're going to do that, we need to normalize by dividing by the amount of charge. So in the same way that if I said to you, hey, would you please carry this rock up a hill, you would want to know how big is the rock. Is the rock 1 pound or is it 1,000 pounds? That's going to make a big difference. And in the same way, we need to normalize. We need to divide by the amount of charge here to say the electric field is going to be the force divided by a positive 1 Coulomb charge. So by tradition, we use a positive test charge, and that is typically going to be a 1 Coulomb test charge. So if we scroll back up to Coulomb's law, let me just remind you of what Coulomb's law had. Coulomb's law had Q1 and Q2 in the numerator divided by 4 pi epsilon 0 r squared a sub r. Well, I'm now dividing by Q2, and I'm just going to call the Q1 just going to be called Q. Everything else stays the same. So all that I did was plug Coulomb's law into the definition of the electric field, and now I get the electric field that surrounds a point charge. And this electric field can either be in newtons per coulomb or volts per meter. There'll be times when each of those are going to be better for us. We're pretty much going to start out with newtons per coulomb, and then as soon as we introduce the concept of voltage, we'll probably switch to volts per meter. So we're going to talk about how Q is not moving. So again, electrostatics, things will get much more complicated for us once the charges start to move. Remember that we started with a positive test charge. So we're going to fix this charge, whether it's positive or negative, we don't know. But when we're testing it, we're going to only use a positive test charge. And so that positive test charge, of course, would be repelled by a fixed positive charge, and it would be attracted to a negative fixed charge. So that means if I put, and let's imagine, for example, that I put a 1 Coulomb charge right here, and the fixed charge is also positive, well then clearly that 1 Coulomb charge is going to be repelled. And more generally, the electric field is going to point away from a positive charge. And in the same way that if I had a positive 1 Coulomb charge here, it would be attracted toward that negative charge. More generally, the electric field is going to be pointing toward negative charges. If we want to get fancy, and often we do want to get fancy, we'll say that electric fields emanate away from positive charges, or point away from positive charges, and they terminate on negative charges, or they point toward negative charges. So we'll also say that positive charges are a source of electric fields and negative charges are a sink of electric fields. This word sink, you think about water going down the drain in a sink, it just goes away. And in the same way that the electric field just goes away when it lands on a negative charge. This idea of sourcing and sinking electric fields is going to be really important to us over the next couple of chapters. We're not going to hit on it so much today, but we're going to come back and talk about it when we talk about Gauss's law. This idea of sourcing and sinking will be extremely important. So let's see a couple of examples here. I have a fixed charge of 3 microcoulombs. So now we're talking about a more reasonably sized charge that is located at 2, 0. So let's just take a minute here and sketch this. So I've got 1, 2, here is my charge, and it's located at, and we got plus 2 microcoulombs. And we know it's located at 2, 0, and we know that the electric field is going to point away from it in all directions. I'm only showing a few of these directions, but there's actually an infinite number of electric field lines that are pointing away from it. So the question is, what is the function E of x, y for the electric field at all points in the xy plane? So we're asking a pretty demanding question here. We want to know, no matter where I look in the xy plane, what is the electric field? So I got some work to do here. This is going to take a little bit of effort. I know that my definition of the electric field for a point charge is going to be Q divided by 4 pi epsilon 0 r squared times a sub r. And I can immediately identify that this Q is going to be 3 microcoulombs. Now, I do need to figure out what is going to be R, what is going to be A sub R, and so forth. Let's go ahead and figure out what is R for a given point. So R is now a function of X and Y. Well, R is going to be how far is this point from the point 2, 0. So what is X minus 2, the quantity squared, plus Y minus 0, the quantity squared. That is the distance of any point in the xy plane to the point 2, 0. And of course, if I were to square that, r squared then is just going to be x minus 2, the quantity squared, plus y squared. So that's going to be pretty convenient. Of course, if y were anything other than 0, then that would have a term as well. I'm going to need to figure out what is a sub r. So a sub r is going to be r2 minus r1 over the magnitude of r2 minus r1. And these are all vectors. And so this is going to be, let me just take a minute and figure out what is R2. So R2 is going to be some point over here, and just sort of generically, I'm showing R2 as this generic point, but R1, of course, is going to be the point that we're actually talking about. So R2 is going to be some quantity x times a sub x plus some quantity y times a sub y minus, now this is going to be 2 times a sub x plus 0 times a sub y. All of this is divided by the distance between those, but we just found the distance between there. It's this quantity right here. And so I'm going to go ahead and in the denominator, I'm going to say this is x minus 2, the quantity squared, plus y squared. And so now I have a sub r. Well, let's go ahead and finish this up. E then, and by the way, E is a function of x and y. This is going to be equal to Q, 3 times 10 to the minus 6th. And I'm going to omit the units because I'm going to keep the units consistent, but if I were using anything other than coulombs, newtons, and meters, I would absolutely include the units as well. So I have 4 pi times epsilon 0, which is 8.854 times 10 to the minus 12th. And then that's going to be multiplied by r squared. Well, r squared we found over here is this quantity, so this is x minus 2 squared plus y squared. And then I have a sub r, and so I'm just going to take this thing, a sub r, and I'm going to plug it down here. So this is x minus 2 times a sub x plus y a sub y, and that's all divided by the magnitude, the square root of x minus 2 squared plus y squared. Now we could leave it like this, but we're better than that. What I'm going to notice is I'm going to notice that this quantity right here and this quantity right here are the same thing. This is to the 1 power, and the square root is to the 1/2 power. So 1 plus a half gives me 3/2. So I'm going to go ahead and combine all of these constants together. So all of these constants, when I multiply them together, gives me 26,963. And then I'm going to have times x minus 2 a sub x plus y a sub y divided by x minus 2 squared plus y squared all to the 3/2 power. And that will all end up being in newtons per Coulomb. So all I need to do is plug in a quantity for x and plug in a quantity for y, and I will then know what is going to be E at that location x comma y. So again, let me just take you quickly through it. I calculated what is r, calculated what is r squared, calculated the unit vector a sub r in terms of x and y. Remember that we have an arbitrary point, and this arbitrary point is at x comma y. And then I plugged all of that into my expression for the electric field, and I ended up with one expression for the electric field. And I see now that there's an error in this very first picture that I drew. Rather than 2 microcoulombs, that should have read 3 microcoulombs. All the calculations in the problem itself are correct. It's just that I made a mistake in the initial figure. What is the electric field at the origin? Just to clarify, the origin is the fancy word that we use for 0, 0, the center of everything. So if x equals 0 and y equals 0, I'm going to plug those into this equation here. And I'm going to end up with the fact that E at 0, 0 is going to be 26,963 times, and now it's going to be x minus 2, which is just 0 minus 2, which is to say just negative 2 a sub x, not a tilde, a hat. And then this y a sub y here, well, that's just going to be 0 a sub y. And then that's going to be divided by x minus 2, which is just minus 2 squared, plus y squared, which is 0 squared, all of this to the 3/2 power. And when I plug all of that into my calculator, I end up with negative 6,734 a sub x newtons per Coulomb. So let's just take a minute here and observe that if we had the origin is here, and I'm going 1, 2 away, here's my point charge. So this is going to be plus 2 microcoulombs, and as we saw earlier, the electric field is pointing away in all the directions, and it's pointing away including here, it's pointing away. So the electric field at the origin is pointing in the negative x direction, and that's what we just found here, the negative a sub x direction. So that's going to, that verifies that we probably did get the direction correct. We'd have to double check the math to see if the magnitude is correct. Now finally, given that situation in those two examples, what would be the force on a charge of negative 4 coulombs situated at the origin? So we now know that there's the point charge over here, and it's causing an electric field, and that electric field is pointing in the negative x direction, but the force is defined to be the electric field multiplied by the charge. And so in this case, that is negative 6,734 a sub x newtons per Coulomb multiplied by negative 4 coulombs, and therefore the force is positive 26,939 a sub x newtons. So although the electric field is pointing to the left, we find that if we're talking about if this now has negative 4 coulombs, then the force is going to be pointing to the right. Just remember that the force, that the electric field assumes a positive test charge. So if you have a negative charge at that point, then the force is going to be in the opposite direction of the electric field. One of the most useful things about electric fields is that they obey superposition. And you've seen superposition in circuits for sure. Superposition in electric fields is basically the same. Calculate the electric field due to each point, add them up, and that will give you the total electric field. So let's look here. We have a system with two charges. One of them is at negative 3, 0, and the other one is at positive 4, 0. So let's draw a little sketch here. So 1, 2, 3. I have a charge that's here, and that's plus 4 millicoulombs. And I go 1, 2, 3, 4, not necessarily to scale. And this one is negative 3 millicoulombs. And the question is, what is the electric field at the origin? So at the origin, what is the electric field? Well, let's call this Q1, and let's call this Q2, and let's think about what is going to happen at the origin due to Q1. Well, Q1 is a positive charge, and we therefore know that the electric field is pointing away from it in all the different directions, pointing away, including at the origin where this electric field is going to point away. So this is E1 is going to be pointing away from that charge. Q2, on the other hand, is a negative charge, which means that the electric fields are coming into that charge from every direction, including at the origin. And so I've kind of got these two electric fields that are each drawn on top of each other. Both of them are pointing to the right. But remember that E1 is being pushed by Q1, whereas E2 is being pulled by Q2. So we have a push and a pull that's going on, and they're going to add up. Now, one thing that we're gonna keep track of then is what happens to each one of these charges. So let's consider the electric field due to the first charge. So E sub 1 is going to be Q1 divided by 4 pi epsilon 0 times R1 squared times A sub R1. Now, I just want to mention here that A sub R points from the fixed charge and toward the point of interest. So we can still do A sub R in the hard way, or in this case we can do it in the easy way. If we say A sub R1 is pointing from the fixed charge, which is Q1 here to the left, and it's pointing toward the origin, well then I know that A sub R1 is just going to be positive A sub x. And I know that Q is going to be 4 times 10 to the minus third over 4 pi epsilon 0. What is the distance, R? R1 is going to be 1, 2, 3 units between Q1 and the origin. So this is going to be 3 meters squared times A sub x. And this then works out to be 3.99 times 10 to the 6th A sub x newtons per coulomb. E2, on the other hand, is going to be Q2 divided by 4 pi epsilon 0 R2 squared times A sub R2. What is A sub R2? It points from the fixed charge, which is now over here on the right, and it points toward the point of interest. So this is now in the negative A sub x direction. So this is negative A sub x. So this is going to be negative 3 millicoulombs divided by 4 pi epsilon 0. That distance is going to be 4 meters squared times negative A sub x. And if you began to panic when I introduced that negative A sub x, now you realize that those two negative signs are going to cancel each other out, and we end up with 1.68 times 10 to the 9th A sub x newtons per coulomb. And then finally, the total electric field is going to be E sub 1 plus E sub 2, which is 3.99 times 10 to the 6th A sub x newtons per coulomb, plus 1.68 times 10 to the, whoops, that's not times 10 to the 9th. Sorry about that. I'm used to these numbers being so big. That's 10 to the 6th times 10 to the 6th newtons per coulomb in the a sub x direction. And this then works out to be 5.67 times 10 to the 6th newtons per coulomb in the a sub x direction. And the math did in fact work out so that the two electric fields are both pointing toward the right and the total electric field is pointing to the right. The question then asks, what is the force on a charge of plus 2 coulombs at the origin? Well, the force is going to be Q times E, and in this case it's E sub t, the total electric field, which is going to be plus 2 coulombs times 5.67 times 10 to the 6th newtons per coulomb, and that's in the a sub x direction, and that's equal to 1.13 times 10 to the 7th a sub x newtons. And because this is a positive charge, the force is in the same direction as the electric field. Let's do one more example. This one's going to have 3 charges rather than 2. We're going to place these 3 charges at the corners, 3 corners of a square. So I'm going to have a charge here, I'm going to have a charge here, I'm going to have a charge here, and then the question is, what is the electric field at the 4th corner of the square? So let's name these 3 charges. We'll call this one Q1, and it's going to be plus 1 coulomb. Could omit the plus there, but we'll go ahead and include it this time. That's Q2, and this is Q3. That's also plus 1 coulomb, and each of these are located 3 units from the origin. Let me try that again. 3 units from the origin. There we go. This one is 1, 2, 3 units from the origin. 1, 2, 3 units from the origin, and then 1, 2, 3. And so the question is, what is the electric field at that 4th corner of the square? Well, if we think about Q1, we understand that because it's a positive charge, the electric field is going to be pointing away. So this will be E1. We understand that Q3 is going to lead to an electric field E3 that also points away, and that Q2 is going to point up and to the right. It'll point to the northeast. And so we know that we need to calculate those 3 components of the electric field, and then we need to add them together to find the total electric field. So let's calculate E1. E1 is going to be Q1 divided by 4 pi epsilon 0 R1 squared times A sub R1. Now, A sub R1 is going to be pointing in the positive x direction. Let's just take a minute here. Let me just give you one quick insight. 1 over 4 pi epsilon 0 is a constant that you're going to be working with an awful lot. To save you some time, I would just say use 8.988 times 10 to the 9th. Or of course, if you can tolerate just 2 significant figures of precision, then you can say 9 times 10 to the 9th. So in this case then, I know that this is 1 coulomb. Again, I'm going to just omit the units because we're using standard SI units and they'll all cancel each other out. The 1 over 4 pi epsilon naught actually turns out to be 8.988 times 10 to the 9th. That'll be up in the numerator, and then divided by R1 squared. Well, what's R1? I have to go 1, 2, 3, 4, 5, 6. So it's 6 meters away, and that quantity is squared. And then A sub R points from the source of the electric field to the place where the electric field is being felt, and so that is plus A sub X. And so this works out to be 2.50 times 10 to the 8th newtons per coulomb in the A sub X direction. E sub 2 is Q sub 2 divided by 4 pi epsilon 0 R2 squared times A sub R2. Now Q2 is still 1 coulomb. The 1 over 4 pi epsilon 0, that's still going to be 8.988 times 10 to the 9th. What is R sub 2? Well, R sub 2 is actually the hypotenuse of a triangle that has these 2 edges. And so if we know that this side is 6 and this side is 6, then this side is the square root of 6 squared plus 6 squared. So I can take the square root of 6 squared plus 6 squared, and then I square that because it's r squared in the denominator. And then multiplied by a sub r2. Well, a sub r2 has an a sub x component, and it has an a sub y component. But if we just left it like that, then it would not have a unit vector. It would have a magnitude that is greater than 1. So we're going to divide this by the magnitude of that numerator, which is the square root of 1 squared plus 1 squared. And when we work all of this out, we get to be 8.83 times 10 to the 8th, or times 10 to the 7th in the a sub x direction, plus 8.83 times 10 to the 7th in the a sub y direction, newtons per Coulomb. E sub 3 is actually very convenient for us because E sub 3 is the same magnitude as E sub 1. Just consider that it's still Q3 in this case, over 4 pi epsilon 0 r sub 3 squared, which in this case is 8.988 times 10 to the 9th, divided by just 6 squared, and now it's in the a sub y direction. If you plug that into your calculator, or you could just recognize it, that this is equal to the same quantity, 2.50 times 10 to the 8th newtons per Coulomb in the a sub y direction. And so then the total electric field, E sub t, is E sub 1 plus E sub 2 plus E sub 3. And that means that it is 2.50 times 10 to the 8th plus 8.83 times 10 to the 7th in the a sub x direction, plus the same thing, 2.50 times 10 to the 8th plus 8.83 times 10 to the 7th, and this one in the a sub y direction. And then this total electric field works out to be 3.38 times 10 to the 8th a sub x plus 3.38 times 10 to the 8th a sub y newtons per Coulomb. That's the electric field. And then we are also asked to find the force, and the force on a 1 nano Coulomb charge. So this is 1 times 10 to the minus 9th coulombs multiplied by 3.38 times 10 to the 8th a sub x plus 3.38 times 10 to the 8th a sub y newtons per Coulomb. And that works out to be 0.338 a sub x plus 0.338 a sub y newtons. So about 1/3 of a newton in the x direction and about 1/3 of a newton in the y direction. And then finally, the last example, imagine that you didn't need to calculate a numerical value, you just wanted to sketch what does the electric field look like. Well, we know that if we have a positive charge and a negative charge, this is known as an electric dipole. And we're going to see electric dipoles quite a lot this semester. They happen naturally, and we also design them as engineers. With an electric dipole, we know that the positive charge is going to have electric field lines emanating away from it. It is a source of electric fields. And then the negative charge is a sink of electric fields. They terminate on the negative charge. So the question you might ask is, what happens in between? Well, these electric field lines tend to be, in the absence of other charges, electric field lines are continuous. And so we could see that this electric field line, for example, probably continues over and goes straight into the negative charge. And then that probably helps us to see that this one curls up and then down. And this one curls down and then up. Whoops, kind of missed that a little bit. Curls down and then up. And then this one curls more, and this one does too. There's some symmetry here. Whether or not my drawing is showing it, there's symmetry here. And then this last one, you could say, well, does it go up or down? Actually, right at that boundary, it's a toss-up, so I'm going to show it two different ways. There's one that goes up, and there's one that goes down. And they both come in on the other side. And then just remember that these electric field lines are always directional, And so the direction is always away from the positive charge and toward the negative charge. So it's helpful to be able to show the electric field lines, sketching them like this. And if you had a more complicated system with 3 or 4 or 5 charges, you could either sketch them, or we can see that MATLAB could be used to sketch what those electric fields would look like. So we covered a lot of ground today, but the most important thing we saw is universal rule number 1. Electric charges always exert a force on each other. If they're the same charge, same polarity of charge, it will be a repulsive force. Positive to positive repels, negative to negative repels. But if they're the opposite polarity, they'll attract. Everything else that we talked about built off of that. We can use Coulomb's law to specify the magnitude of that force. We can use the electric field to consider not 2 charges, but only 1 charge. And we're going to say what would happen if we removed the second charge and then we imagined or we conceived of a charge that we would place at every point around the first charge. And electric fields always point away from positive charges toward negative charges, and electric fields always obey superposition. In other words, the electric field at a given point can be calculated as the sum of the electric fields due to all of the surrounding charges. Today, those summations have just been for discrete charges, but next time we'll see what happens if it's a continuous charge.